All right, so from previous week, we have been working on 6.2, the mole and the chemical formula. So first of all, we defined mole and we discussed how we formulate mole, discussed its formula and different rearrangements along with the perspective of a Gödel's constant. And we calculated how to calculate the MR, everything. Now, from moving on from moles, we were supposed to go for empirical and molecular formulae. So for past couple of days, what we have been doing is how different cases of empirical formulae are used in exams for Cambridge or for molecular formulae. And yesterday and the day before yesterday, we have been practicing this stuff. So now, after doing all of this, we come to 6.3, the mole and the chemical equations. Now, since we understand how the formula for mole works, how we calculate the empirical formula or the molecular formula, so we can actually put that to practice for complete chemical equations and we can work stuff out. Now, the mole and the chemical equations, this topic itself is actually bifurcated into two parts. The first part is rather easier, and we just try to go with the simpler ratios, what has seemed to come across us from the mole and the chemical equations portion, looking at looking at an equation, a balanced chemical equation. We can always have the idea about the stoichiometric ratios, how they work, and we can work out the number of moles or maybe even the masses. So we're going to take a few examples over here and we're going to discuss them. Let's get started. For the most basic example, they considered an example which might seem really easy to you. Take a look at this one. And I'm going to change the color before I move. Okay, take a look at this example. This is pretty easy. Iron, when reacts with sulfur, gives us iron sulfide. So much so we understand that this equation is already balanced. We have 1 mole of iron reacting with 1 mole of sulfur, forming 1 mole of iron sulfide. So even in case of moles, this is pretty easy. 1 mole for this one was added to 1 mole for this one, and we formed 1 mole of our product, iron sulfide. So it's pretty easy. But if I convert these moles into masses, you're going to understand that 56 grams of iron reacts with 32 grams of sulfur and produces 88 grams of iron sulfide. Now, this is actually following law of conservation of mass. If I complete it, this is law of conservation of mass. If you're going to pick up a calculator and you're going to add these two numbers, 56 and 32, you get the answer of 88, which gives you the idea that the masses of the reactants, actually the sum of all the masses of the reactant is equal to sum of the masses of products, which is actually shown over here. We're going to take a couple of more equations and we're going to do the same thing to understand that how the equations for moles or the equations for masses work. Now remember, when we write a balanced chemical equation, we actually give the hints for moles. For masses, what we need to do is to actually refer to the periodic table, calculate all the MRs, and place them as per the equation to get our answer. Now, he is going to explain to us that this ratio for iron and sulfur, for example, iron was actually 56 and sulfur was actually 32, giving us 88 grams when they were added. Now, this ratio can be worked in smaller or bigger portions. For example, instead of taking 56, if we take 5.6 grams, and instead of taking 32, if we take 3.2 grams, the answer won't be 88 grams anymore. It would also be 8.8 grams, which means that the ratio, no matter how smaller or how bigger we're going to convert it into, it would always remain the same. Do you understand this specific point?
Yes, sir.
Good, great. Which means that if we talk about something differently, and I'm going to put up a different example just to make sure that you got the point and you can really change it to many different kinds of ratios they can come up with. So instead of considering 5.6 or 3.2 or 56 or 32, let's say, what if we consider 560 grams for this one, 320 grams for this one? How much mass are we going to get over here? You may use your calculator, take a minute. You can answer the question after you're done with the calculation.
Sure, it would be 80.
Correct. That's it. So I hope you completely understand what we have been doing over here and how we are actually going with the psychometric values or the balanced chemical equation to actually help us with any kind of calculations. Now, these calculations at the very start were pretty simple and pretty straightforward as per the periodic table. But when we keep changing the values, you understand how to solve them, how to get your answer. So let's go with a different equation and understand this thing more with somewhat a different example. Now this time the equation has been changed to calcium carbonate's equation. It is going to form calcium oxide and carbon dioxide when we're going to thermally decompose it, which means we're going to break it down with the help of heat. When we heat calcium carbonate, it is converted into these two products. Now the equation has already been written. And if we look at this equation, we need to first make sure that the equation's balanced. So let's understand it. We have one calcium over here, so one calcium over here. We have one carbon atom over here. We have one over here, and we have a total of three oxygen atoms here. One is over here and two are over here, so a total of three oxygen atoms, which means the whole equation is already balanced. We do not need to work upon it. Now, if we take a look at it, 1 mole of this reacted with 1 mole of calcium oxide and actually produced 1 mole of calcium oxide and produced 1 mole of carbon dioxide too, which is also given over here. So this is the balanced chemical equation, which is giving us the idea how the molar ratios between these are going to work. So if we work out the MRs and take a look in this section, he's going to work out the MRs. The MR for calcium carbonate is 100, that for calcium oxide is 56, and for carbon dioxide is 44. If we take these values simply in grams, it would be really understandable for us. As per the previous example, we are literally doing the same to this example. I hope you get the idea, right? Do you get the point?
Sir, I'm kind of confused. Why are we why is it why are we trying to find the MR like 40 plus 12 plus all that?
The
Aren't we
MRs
just gonna
actually.
find
Go ahead.
wait, so these are just the masses and we're multiplying all those because they're a compound and we're getting the answer.
Yeah, they are compounds and we're getting the answer. This means this actually gives this and this. If I do this, something like this would be really more understandable, which means when we break down 100 grams of calcium carbonate, it gives us exactly 56 grams of calcium oxide and 44 grams of carbon dioxide. So the mass, the law of conservation of mass, and I'm going to complete it by writing it over here, law of conservation of mass still stands. So if you're going to add up 56 and 44, the answer would be 100. So it's telling you whichever way you're going to work it, either you're going to work from reactants to a product, or you're going to break a product down back into its reactants. It's every time going to be the same in terms of mass. The mass would be conserved. There would be no loss in mass. There would be no gain in mass. It would actually be exactly be equal. The sum of the masses of reactants or the sum of masses of products is exactly going to be equal every time. And we actually don't just go with this piece of information. What we are about to do, and this is going to exactly answer your question, which you were just asking. We can always work this out by scaling it up to bigger values, or maybe scaling it down to smaller values, which we have done before with the example of iron sulfide previously. So let's scale it up. If instead of 100 grams, I'm going to talk about 100 tons, it's really going to end up in the same set of numbers, but just with a different unit. So these ratios, these numbers actually help us a lot to work. And if you didn't know how much are we are going to get for calcium oxide or carbon dioxide, since you already have these ratios, you can work them out. And I am going to quote more examples to actually explain to you how you're going to do that mathematically in exams for questions that are unknown to you. Since this question has already been solved for you, so it might not make that much sense. But for the questions in which we have unknown values, are we going to work them on the same basic principle as we have in front of us right now? You are going to know how we work them out. And it really actually works for everything we do in our daily life. Okay, let's take your example. I'm going to take an example out of a daily life to give you an idea how we work out these values. Okay, let's suppose you go out, you go to a clothing store, you actually like a couple of t-shirts. Now you go on to asking about the price, and there is a discount. You work your way out, and you understand that a specific shirt, I don't know, I'm just quoting it as an example, I'm assuming this specific shirt is like 50 riyals, and you like three shirts of that sort. How much are you going to pay in total?
So it would be 150.
Right. So what are you doing? Actually, to answer your question correctly back to me, what you did was a simple multiplication step. You multiplied the number of shirts with the amount of one shirt to get them out of all the shirts, right?
Yeah. Yep.
Okay. So you have been doing the same thing over there. So once you know that 100 of this is going to give you 56 of this and 44 of this, no matter what the units are, keep changing the units. You can scale it up, you can scale it down, you can talk about very minute values, you can talk about very big industrial sort of values. So if you know these numbers, it's really easy to work your way out about the amount of calcium oxide or carbon dioxide being produced every time, no matter how smaller you're going to do it in lab or how bigger of a scale you're going to do it in industry. Make sense?
Sir, but I have a question. Like, sir, this is totally hypothetical, right? There is no loss of energy counted in in these experiments, right?
Loss of energy or loss of mass? Since we haven't talking about energy in this whole case, the whole thing we have been talking about in terms of conservation was mass. And yes, this is
Sir, if you
hypothetical.
do it, if we do the experiment in real life, sir, there will be, some energy lost by emitting by light or by heat, right? So we won't really get the perfect, separation,
Okay,
or would it be the other way around?
yes, you are right. First of all, you're right. But why have we have been discussing energy since everything we have been talking about is math? Okay, I think you want to you might want to still put it like that. Yes, if we talk about in terms of energy, yes, you can't really convert all of your input energy to all of the output. There is definitely waste of some energy. And yeah, that waste can be in the form of light or in the form of sound or maybe in the form of some mechanical or chemical energy wasted. Completely understandable. Yes, you're right. So this is hypothetical. So when we are doing hypothetical work, we like to keep it ideal in order for us to easily calculate our numbers. See, if even with hypothetical calculation, you keep counting the factors, the calculation is going to become a lot complicated, which in case of students, we don't do, not at least at this level. Now, this may answer your question, right?
Yes, sir.
Great, great. So now if you understand how we scale these numbers up or how we scale them down, so I think it's pretty easy. So we can move up to for some whiteboard work. What I'm gonna do is that I'm gonna open up the whiteboard, and since we are doing mole and chemical equations, we're gonna go with that. Okay, so I'm gonna pose the same question over here. So let's write the equation first. So to begin with, I'm going to go with the same equation. We have calcium carbonate and we heat it up, and in turn we get some calcium oxide, and we also get some carbon dioxide. Now, the question really is, how much calcium oxide is produced in the how much calcium oxide is produced in kilograms if 2.3 kilogram of CaCO3 is thermally decomposed. Now, what would you do with this kind of question? Okay. Now, I hope you understand what the question is about. The question is about that we are going to calculate the amount of calcium oxide produced, and that too in kilograms, not just in grams, if we're going to decompose 2.3 kilograms of calcium carbonate. Now, with this kind of question, what you're supposed to do is that, first of all, balance the equation if it's not balanced. For the thing that you are given the values for, you need to calculate them. Now, you have been given with 2.3 kg of this, and you don't know about this one, which we are supposed to calculate. Now, if I know the MRs, then I understand 100 of this would give us 56 of this that we did previously on the book. So I'm not going to go for all the calculations, and 44 of this. So it's really easy. What you need to do, this is what you calculate, okay? So really, the step I want you to focus at is that you have the information for calcium carbonate. Let's put it on the left. You want to find out the information for calcium oxide. So let's put it on the right. Okay. So 100 grams of this gives you 56 grams of this. That's why MRs are important, because MRs are going to be our first step. Okay. And when you have 2.3 kg of this, how much would you get this? Okay. That's really what the question is all about. What you can do for calculation is that you, instead of putting a question mark over here, let's put it as x. Divide this with this. X goes over here. This goes over here. This comes over here. Really make a little bit of changes. 56 grams multiplied by 2.3 kilograms over 100 grams. So x went over here, 100 came as a denominator on the other side, 2.3 kg goes to the numerator on the other side. Gram, gram, cut them out. You can solve the rest simply with the calculator and you'll have your answer. If you have the calculator with you, help me a little bit, calculate it for me, and let me know what the answer is. So what happens
Sir,
if you
it's
divide?
one. Sir,
Okay,
it's
go
one
ahead.
point 288.
It's 1.288. And since we have this unit still over here, 1.288 kilograms. That's your answer. That's what you're going to get as in mass of calcium oxide. There you go. You have your answer. Now, if the method is clear to you, then it shouldn't be a problem if I change the question with some different values.
Yes, sir.
So shall I go ahead and give you different questions?
Um, sure.
Okay, let's get started. So if we consider this one as question number one, I'm going to write question number two over here. Okay, using question number one equation, how much CO2 is reduced in I made a mistake actually in grams if 25 grams of CaCO3 is decomposed. Okay, go ahead with this one. Since you already have the equations, you have the MRs, you can simply go for the ratio step, which is done at the center bottom of your screen right now. That's perfect. The answer is 11. So you just changed the whole ratio with calcium oxide. Instead of that, you took carbon dioxide. So I hope you have done the same. So calcium carbonate is taken in ratio with carbon dioxide this time, not calcium oxide. And since 100 grams of this produces 44 grams of this, what if we don't go with 100 grams? What if we just go with 25 grams as stated in the question? So instead of 100, we have 25 grams over here. What are we going to produce over here? We don't know. So we're going to put it as X. So you divide both of them. This goes over here. This comes over here. This also goes over here. So X is equal to 44 grams multiplied it by 25 grams and over 100 grams. So yeah, we cancel out grams and grams, and 25 1, 25 4, it's really easy. 4 ones are 4, 4 11s are, so this is actually 11 grams. So actually X was, what was X? X was mass of carbon dioxide. So mass of carbon dioxide is 11 grams. So I hope you have done the same, right?
Yes, sir.
Great. Now, why do we give you this ratio method? This ratio method is really extremely easy. Not just easy, it's also fast. So what you can do is that whenever you have the whole equation and you have the same units or same quantity to go with, means all of this is considered for the units in math. Whether that's grams, whether that's kilograms, or whether that's tons, it really doesn't matter because all of it is taken for the unit of masses. Now, in case of masses, if you have to take mass on the left or the right of the equation, it's really easy. You can always work it out with the help of this ratio method. So this is commonly known as ratio method. And in some books or reference books, you might see it as metric method. Yeah, both names exist and both names mean really the same thing, the same process, and you understand what to. Now remember, for the stuff that you have been given the information about is always taken on left, like in this case, that would be calcium carbonate. We already know we have 25 grams of those. And for something that you need to calculate and which is hidden or actually is a part of question, that is always considered on the right. That's a good way to do it. If you actually set up your parameters to place them at specific places, so you're going to do it that every time with the any question. And since you'll be uniform, you'll actually be doing everything correctly without making up a mess or without confusing yourself. Okay, I hope that all makes sense to you, right? Good, good, great. So let's just continue and let me give you another question. Just give me a minute to reset my whiteboard. I'll be back in a minute. All right, let's. Potassium chlorate is usually thermally decomposed or decomposed to KClO and Cl2. So, sorry, my bad, not Cl2, O2. Okay, as KClO3 gives us KClO plus Kc plus O2. So what amount of, let's go with it. So what amount of KClO and that in grams will be received if 100 grams of KClO3 are decomposed. Now for this question, you need to go with the same set of steps. One, balanced chemical equation. Okay. Number two, calculate MRs. Number three, apply the ratios. So that's what you are going to do every time. So that's a great key to solve these questions. Go ahead, solve this one out. I can wait. What I'm going to do is that I'm going to write your solution over here and I'm going to discuss your mistake with you because there is a very small mistake in it. So that's very good to begin with, that you wrote off the equation at the top. And then really what you did back there was that if you have 100 grams of this how much you get out of it. And when you noted down the MRs, that's 122.5. And I haven't calculated it myself, so I'm just going to assume that whatever you calculated is right. And this one is 90.5. I hope you took potassium as 39. You took chlorine as 35.5, and you took oxygen as 16 from the periodic table. If you have taken these values, yes, you were right. So this is what you got, and then actually it was 100 over 122.5, what you have written, and then it's equal to x over 90.5, the complete division. Now, the mistake you made over here is x is already here. So you just need to take this one over here. So x would become 100 multiplied by 90.5 divided by 122.5. That's what this becomes. X is already on top. Why would we move X? We just need to move 90.5. So if you do it this way, you'll see that the answer you got is actually a little bigger. You'll get a smaller answer. Try going with this calculation. Let me know what you get.
So I'm getting 73.87.
73.87 grams of KClO. And that's the correct answer. Okay.
Yeah, I just made a silly mistake. Yeah, sorry, sir.
Yeah, that's fine. That's a really small mistake compared to what we have done today. So yes, which gives me the idea that you would be able to do it correctly next time. Okay. So
Yes, sir.
I think that's about it for today.